Unhappy vertices and artificial spin ice, new degeneracies from Vertex-Frustration. In this paper we solve a long-standing problem for artificial spin ice. We show how to create artificial spin ice with extensive residual entropy, not by exploiting degeneracy at the vertex level, but with a new frustration in allocating vertices on the lattice. First, let's start with some historical context by considering Pauline's work on water ice. The location of hydrogen in crystalline water is given by the so-called ice rule, too nearby and too far away from each oxygen, which ensures charge neutrality within each tetrahedron. The configuration is clearly not unique, and this enormous degeneracy leads to residual entropy at low temperatures, which Pauline estimated with a simple calculation. The key point is that Pauline's estimate is entirely local, depends only on the ice rules around a single oxygen, and does not directly depend on the configuration of next nearest neighbors and beyond. An equivalent description with arrows captures the ice rule as 2 in, 2 out for each tetrahedron. This is a convenient picture for spin ice, a family of crystals in which the arrows represent rare earth magnetic moments. Artificial spin ice, or ASI, was proposed as a two-dimensional analog to 3D spin ice. Projecting the pyrochlore lattice into 2D yields a simple square lattice. However, this breaks the degeneracy of the ice rule, and so square ASI has a unique, perfectly ordered ground state. While a variety of workarounds have been proposed, it seems unsatisfying that most ASIs lack one of the fundamental properties that made natural spin ice interesting. Here we propose a general method to engineer a limitless number of ASI lattices with massively degenerate ground states. Our recipe exploits geometric frustration to construct a new sort of frustration, which we call Vertex-Frustration. How does this work? In the square ASI ground state, even though pairwise interactions are frustrated, the lattice still allows every vertex to be in a minimum energy configuration with perpendicular spins nose to tail and collinear spins anti-parallel. Similarly, in spin ice, every tetrahedron in the lattice can simultaneously be in an ice rule configuration. Now, consider a vertex-frustrated lattice. The mutual arrangement of vertices means not every vertex can be in its lowest energy configuration. Somewhere on this loop, there has to be an unhappy vertex. It must take on a higher energy configuration. While these unhappy vertices appear to be excitations, they are not. They are part of the ground state and cannot be removed, as we prove in the paper. We also prove some general rules to distinguish vertex-frustrated and non-frustrated lattices without knowing the ground state, since finding the ground state structure is usually not obvious. It turns out these rules also help in constructing ground states. How does vertex frustration lead to extensive residual entropy? There's enormous freedom in where to place these unhappy vertices, with many possible choices giving the same energy. Also appealing is that one can construct an essentially infinite library of vertex-frustrated lattices, which can be designed with certain interesting properties. We merely set out to create ASI with extensive entropy, but along the way we found that many other interesting properties came along for free, such as monopole crystallization, spontaneous symmetry breaking, and smectic-like phases. This example presents so-called monopole crystallization in analogy with hexagonal ASI. 3 island vertices appear to carry magnetic monopoles, and long-range interactions between these monopoles will partially break the degeneracy of the ground states shown previously. Arrows depict a chirality associated with each supercell. The only possible tilings of supercells break the lattice's rotational symmetry to produce a smectic-like phase with sliding symmetry. For contrary examples, these lattices cannot form monopole crystallized configurations. To satisfy the pseudo-ice ground state rules, the circled nearest neighbors are forced to carry like charges. This example also exhibits a sliding phase in which ordered backbones separate disordered staircases of spins. It also features a monopole crystallized ground state. To see more, I encourage you to read the paper.